This video is about how to create and interpret graphs of the sine and cosine functions. It corresponds to material that can be found in section 6.4 of the textbook. We begin with sine of theta, which is a function of theta. As is true for any function, we can change the variable that we use as the argument of the function. Here we replace theta with x, and we note that f of x equals y. By expressing this function in terms of x and y, we can now graph the sine function in the xy plane. In the last section, we determined the sine function for a variety of angles. Some of these angles, expressed in radians along with their sines, are listed in the table on the left as xy pairs. We can plot these pairs in the xy plane for values of x between 0 and 2 pi. We already know from our study of trig functions that the sine of x is periodic with period 2 pi. We use the letter capital T to stand for period, so what we have plotted here is one cycle of the function y is equal to sine x, or sine x on the interval 0 to 2 pi. But we can graph y equals sine x for other values of x as well, as shown here, taking advantage of the periodic nature of the function to help us. Y is equal to sine x is a function that exists for all values of x, so its domain is the set of real numbers. And we see from the graph that the range of sine of x is between -1 and 1. We can also see from the graph that sine of x is an odd function because it is symmetric about the origin. As mentioned before, sine of x is periodic with period 2 pi. The x-intercepts occur every pi radians at -pi, 0, pi radians, and so on, and there is only one y-intercept at 0. The function has a maximum value of 1 that occurs every 2 pi radians at, for example, x equals pi over 2, 5 pi over 2, and so on. We can graph many other sinusoids by using transformations. Let's begin with the graph of y equals sine of x. If we multiply sine of x by 3, we perform a vertical stretch, which means the amplitude of the transform function is 3. In this graph, it looks like it's been transformed horizontally as well, but it hasn't. Note that the scale on the x-axis has been compressed. Let's look at another transformation, again beginning with the graph of y equals sine of x. First, we'll multiply sine of x by -1, obtaining minus sine of x. The graph of minus sine of x is a reflection of the graph of sine x about the horizontal axis. We note that the period of minus sine of x is 2 pi, the same as the period of sine of x. To graph minus sine of 2x, we perform a horizontal compression of the graph, so that the period is now pi, half of what it was before. And now we have the graph of y is equal to minus sine 2x. As was true for the sine function, we can use x as the argument of the cosine function and say that y is equal to cosine x, where x is expressed in radians. We already know what the cosines of some angles are, and selected ones are listed along with their corresponding angles in the table on the left. These angle cosine pairs can be plotted in the xy plane as shown here for x between 0 and 2 pi. Cosine x is periodic with period 2 pi. And we have graphed it here on the interval 0 to 2 pi. Once we know the values of the function cosine x over one period, we can plot the function for any values of x, as is shown in this graph. This graph shows cosine x for all values of x. We can see that the domain of x is the set of real numbers, and the range is between -1 and pi, as was true for sine x. It's apparent from the graph that the cosine of x is symmetric about the y-axis, making it an even function. We already know that cosine x is periodic with period 2 pi, and that the x-intercepts occur every pi radians at x values such as minus pi over 2, and so on. There is only one y-intercept at y equals 1. The maximum value of cosine x is 1, and it occurs every 2 pi radians at minus 2 pi, 0, 2 pi, and so on. The minimum value also occurs every 2 pi radians at minus pi, and so on. We can use the basic graph of y equals cosine x to help us graph other similar sinusoids by using transformations. Let's begin with y equals cosine x. We can perform a vertical stretch by a factor of 2, which increases the amplitude of the function. Now we have the graph of 2 cosine x. To graph the function 2 cosine of 3x, we perform a horizontal compression of this graph by a factor of 3. The result is shown on the right. Note that the period of this new function is 2 pi over 3. Now let's look at the graph of y equals cosine x, shown here in pink, and y equals cosine of x minus pi over 2, shown in blue. The latter graph is a horizontally shifted version of the first graph. They're plotted together on the same graph. When we graph y is equal to sine x, shown on the right, we see that its graph is identical to the graph of cosine of x minus pi over 2, shown on the left. This means the two functions are equal to each other, and it confirms what we've already seen, that sine and cosine are very similar functions. Performing transformations is one way to graph sinusoids. Another approach is to use what are called key points. We begin with the graph y is equal to a sine x, which has a period of 2 pi. Let's take the interval 0 to 2 pi and divide it into 4 equal subintervals. We then find the value of the function at 5 key points, namely the endpoints of all the subintervals combined. We use these function values to form 5 xy pairs, which, since this is a sine function, are the maximum and minimum values plus 3 points where the function crosses the x-axis. Once we have these 5 key points, we can graph one period of the function and then repeat the pattern over other intervals of period length. The 5 key points of sine of x and cosine x on the interval 0 to 2 pi are shown here. Now let's look at the general function y is equal to a sine omega x, where omega, the angular frequency, is positive. We say that the amplitude of the sine function is the absolute value of a, so that the range of the function is between minus the absolute value of a and the absolute value of a, written that way because a could be negative. Based on examples of transformed sinusoids we've already seen, we know that the period is equal to 2 pi over omega. This means that the interval 0 to 2 pi over omega contains one period of the function. We can divide this interval into 4 subintervals and identify the key points which allow us to graph the function as shown in the figure. Now, given the function 3 sine of 4x, how can we graph it using key points? We know that the amplitude is 3, and we obtain the period by dividing 2 pi by omega, the angular frequency, which is the coefficient of x. Here that means that t is equal to pi over 2. We graph this sine function on the interval 0 to pi over 2, and we obtain this graph as shown. Note the 5 key points are included. Since we graphed a full period, we can graph the entire function by repeating the period as shown. Now let's look at another example where we use key points and transformations to graph a more complicated function, beginning with -4 cosine of pi x. We see that a is equal to -4. So what does that mean for the graph? It means that the function, the basic cosine function, is reflected about the horizontal axis, and we need to keep this in mind as we proceed. We find that the period is 2, and this is enough information for us to be able to graph one period of -4 cosine pi x on the interval 0 to 2. So we see that rather than having the maximum value at x is equal to 0, there's a minimum value there, and the maximum value occurs halfway through the period. And this is because of the minus sign in front of the amplitude. Once we've done that, we can extend the graph horizontally in both directions. Then we can take this function and perform a vertical shift of -2 on the graph, resulting in the graph of the function -4 cosine pi x minus 2, which is shown on the right. We now have a couple of techniques that we can use to graph sinusoidal functions, but sometimes what we want to do instead is to begin with a graph and determine what function is plotted. For example, let's consider the graph of the sinusoid shown. We note that a maximum value occurs at x equals 0, which means that it is a cosine function, and that it is symmetric about the horizontal axis, meaning that there is no vertical offset. The period is 1, which means that the angular frequency is 2 pi. We also see from the graph that the amplitude is 3. Based on all this information, we can write the function as 3 cosine 2 pi x. Now, if instead we have the graph that is on the right, we see that this is an odd function and that it is a sine function that is reflected about the horizontal axis. This means that it is of the form -a sine omega x. The period is 4, which means that the angular frequency is pi over 2. We also see that the amplitude is 2. Based on all this information, we can state that this is a graph of the function y is equal to -2 sine pi over 2 x.